Hello, hello. Last time we looked at parabolas, and now we're going to look at another kind of conic, ellipses. One reason ellipses are important, one place they occur in nature, is orbits of planets around the sun, moons around a planet, things like that typically have the shape of an ellipse. So the orbit of the Earth around the sun is not a perfect circle with the sun at the center. Instead, it's a little bit longer in one direction than in another, which makes it an ellipse. So an ellipse is kind of a stretched out circle. It is a conic, which means you could get it by intersecting one of these cones with a flat plane. You can have ellipses that are taller than they are wide, or ellipses that are wider than they are tall. They could be vertical or they could be horizontal, or they could be sort of diagonal at an angle, although we won't study those because the equations get more complicated and it's a lot harder to tell from the equation what the ellipse looks like. So here is one example of an ellipse. Let's take a look at this and get a feel for some of the parts and properties and things associated with an ellipse. First of all, the center is the point right in the middle of the ellipse. For this particular ellipse, the center is the origin, the point 0, 0. And with a circle, you can talk about the diameter of the circle, which is the distance all the way across from one point on the circle through the center to a point on the other side. And if you are dealing with a perfect circle, it doesn't matter where you go, horizontally, vertically, at an angle, the diameter is always the same length. But with an ellipse, the distance across the ellipse does depend on where you go. So the longest distance across the ellipse from the 2 points on the ellipse that are farthest apart from one another, we call that line segment connecting those two furthest points the major axis of the ellipse. So that's sort of like the longest possible diameter or the longest possible line segment running from one side of the ellipse through the center point to the other side. So in this particular ellipse, the major axis is horizontal and it has a length of 10 units. Then perpendicular to that, we have the minor axis, and that's the shortest distance across the ellipse from one point through the center to another point. And with this particular ellipse, the minor axis is vertical and it has a length of 6 units. The points at the ends of the major axis, those are the points on the ellipse that are furthest away from the center, and those are called the vertices. If you have just one, you say it's a vertex, the plural is vertices, and with this particular ellipse, we have a vertex here at 5, 0, 5 units to the right of the center, and the other vertex is here at negative 5, 0, 5 units to the left of the center. The points at the end of the minor axis are sometimes called covertices. That word isn't used as often, but it is used sometimes. So we have a covertex at 0, 3 and a covertex at 0, negative 3. Now, in the discussion that follows, we're going to be using the letter A, lowercase a, to stand for the distance from the center of an ellipse to either one of the vertices. So from the center to the vertex is A. With this particular ellipse, that would be 5. And so 2 times A would be the length of the major axis from one vertex all the way across the ellipse to the other vertex. And we will use the letter B to stand for the distance from the center of the ellipse to one of the co-vertices. So 2 times b would be the length of the minor axis. So if you start at the center and go a spaces away, you get to one of the vertices, one of the points on the ellipse that's furthest away from the center. And if you start at the center and go b units away, then you get to one of the points on the ellipse that's closest to the center. The eccentricity of an ellipse is sort of a measure of how elongated or uncircular the ellipse is. For any ellipse, the eccentricity is going to be a number between 0 and 1. The closer to 0 the eccentricity is, the more nearly circular the ellipse is. If the eccentricity were 0 exactly, we would have a perfect circle. And if the eccentricity is just a little bit bigger than 0, we have something that is close to a circle. It's maybe a little bit wider than it is long, but the bigger the eccentricity gets, the more elongated the ellipse is, and the more of a difference there is between the major axis and the minor axis. So here are a few examples of ellipses with different eccentricities: 0.25, 0.5, 0.75, 0.9. An ellipse has 2 points called foci. Each one would be a focus, and then the plural of that is foci. The foci of an ellipse are points that are inside the ellipse on the major axis. With this particular ellipse, there is a focus here at 4, 0, and a focus here at -4, 0. And I will tell you what the significance of those focus points is in just a couple minutes here. But for now, they are points inside the ellipse along the major axis. So one of them is if you start at the center and go, in this case, 4 spaces to the right. And the other one would be if you start at the center and go 4 spaces to the left. The bigger the eccentricity, the farther apart the 2 foci are. And then we're going to be using the letter C to stand for the distance from the center to the focus, to either focus of the ellipse. So A is from the center to a vertex, B is from the center to a covertex, and C is from the center to either one of the foci. And there's a relationship between those numbers. For any ellipse, a squared is equal to b squared plus c squared. And that should remind you of the Pythagorean theorem. And so if I draw in a little right triangle here where their sides are b and c and the hypotenuse is a squared is equal to b squared plus c squared. So what that's telling us is that the distance from the covertex to the focus, here to here, is exactly the same as the distance from the center to the vertex, here to here. And for any ellipse, the eccentricity is always c divided by a. So for this particular ellipse, c is 4, a is 5, so the eccentricity is 4 over 5, 4/5, or 0.8. And in this ellipse, you can see that b squared is 9, c squared is 16, b squared plus c squared is 25, and that is a squared. Now, there are 2 ways of defining what makes an ellipse. What do all the points that make up an ellipse have in common that makes them an ellipse? So one possible way of defining an ellipse is this. Start with a point F to be a focus, and a line L to be a directrix, and pick a number E between 0 and 1 to be the eccentricity. Then the ellipse with that particular focus, directrix, and eccentricity is the set of all points P such that the distance from P to F is equal to E times the distance from P to L. So that means for every point on the ellipse, the distance from that point to the focus is E times the distance from that point to the directrix. If we left out the E times part, that would be the definition we saw last time for a parabola. So in a way, if you pick 1 for the eccentricity, then you no longer have an ellipse, instead you have a parabola. The other way you could define an ellipse is start with 2 points to be the foci, and start with a fixed positive number A, and then the ellipse with the foci that are the points you picked, and the major axis whose length is 2 times A, would consist of all points P, so that the distance from P to F1 plus the distance from P to F2 is 2A. In other words, by this definition, what all points on the ellipse have in common is that the sum of their distances to the two foci is a constant. So let me show you a demonstration of how that works. And I'll put a link to this on Canvas so you can try it out for yourself. But here we see an ellipse with the foci labeled. Here's F1, here's F2. And then for any point on the ellipse, this orange line labeled A is how far that point is from focus F1. And this green or this blue line labeled B is how far that point is from the second focus, F2. But if you add those together, they always add up to the same amount. A plus B is always constant, and it's equal to the length of the major axis of the ellipse. So as we go around the ellipse, A might get longer or shorter, and B might get longer or shorter, but A plus B, those two added together, is always exactly the same length for every point on the ellipse. I'm going to drag the foci closer together, and that's going to make the ellipse more nearly circular, or I could drag them further apart, and that's going to make the ellipse less circular and more eccentric. But either way, the distance from focus to point on the ellipse to other focus is always constant. And that means that you could actually draw an ellipse by sticking 2 thumbtacks into a sheet of paper and taking a piece of non-stretchy string and sort of making a loop around it so that the string goes around the 2 thumbtacks, and then you put a pencil and you trace around so that the distance from here to here is always the same as you go around, and you trace out the points that make up the ellipse. Okay, I'm going to end this video here, and I'll come back in part 2 to talk about what the equation of an ellipse looks like and how all these things that we've been talking about relate to the equation.